Today I am going to be introducing a new type of distribution, the sampling distribution. There are actually many types of sampling distributions. Instead of plotting raw values like x-scores, we plot all the possible sample statistics that could come from a given population. So we could plot a sampling distribution of the range, or of the median, or the standard deviation, and so on and so forth, any statistic we observe. But the sampling distribution of most interest to us is the sampling distribution of the means. This distribution, the sampling distribution of the means, is a frequency distribution of the means of all possible samples of a given or controlled sample size. A few key things to remember here. The sampling distribution requires that all samples have the same size. So from a population, I might be interested in plotting all the sample means that have a sample size of 30. We are going to be talking about this distribution in terms of the three features of a distribution we always discuss: its mean, its standard deviation, and its shape. The mean of this distribution gets labeled as mu sub x bar. Because this is a sampling distribution of the means, its mean is the mean of all the possible sample means of a given size that could be pulled from a population. In short, it can be called the mean of the means. And it turns out that the mean of the sample means is always equal to the population mean. So the mean of the means equals the mean. Next, I want to talk through what this idea of all possible sample means and illustrate how the mean of the means equals the population mean. Imagine a very small population of 4 people. In this case, the population of 4 TAs that helped me teach a section of Psych 3990 a few years back. If we were going to pull every possible sample of 2 people from this population, you can see that would produce 6 different samples. Julie plus Jessica M, Julie plus Jess, Julie plus Tatapa, Jessica M plus Jess, Jessica M plus Tatapa, and Jess plus Tatapa. That's every possible combination of 2 people. Here is the height of each member of our population in inches. The average of this population is 64.75 inches. We can also calculate the mean of each of our possible samples, the x-bar of each sample, where x-bar equals the sum of the scores in the sample divided by the number of people in that sample. And if you take the mean of all of these sample means, the mean of every possible sample, that value will be equal to the population mean. Next, we need to talk about the standard deviation of the sampling distribution. This special kind of standard deviation is called the standard error. Its symbol is sigma sub x bar. The standard error tells us about the average distance of sample means from the mean of means. This special kind of standard deviation is called the standard error. Its symbol is sigma sub x bar. The standard error tells us about the average difference of sample means from the mean of means. The variability in the sampling distribution of the means is about how spread out the sample means are. The formula for the standard error is the standard deviation of the population divided by the square root of the sample size. This formula shows us that 2 factors affect the standard error. First, the standard deviation. The more variability there is among the population of raw scores, the more sample means that come from that population will differ. The second is the sample size. The bigger the sample size, the less the sample means are going to bounce around. So to wrap up, the standard error tells us the average distance between any given x-bar and mu sub x-bar. Next up is the shape. The shape of the sampling distribution changes depending on the sample size. But overall, it resembles a normal distribution. In fact, there are 2 conditions under which the sampling distribution becomes so normal that we go ahead and call it normal. The first of these is about the population scores. If the raw scores are normally distributed, then a sampling distribution that comes from that population will also be normal. The second time a sampling distribution is considered normal is if the samples have at least 30 people in them. In this case, the sample size is big enough to balance out any outliers or unusual scores, and the sampling distribution of the means becomes normal. Let's do a quick learning check. Consider a population of students who have taken the GRE verbal section. Their scores are approximately normally distributed with a mean of 400 and a standard deviation of 100. What would the characteristics of a sampling distribution of all possible means of n equals 50 be? First, what would its mean be? Its mean would be 400 because the mean of the sampling distribution is the same as the population mean. What would its standard deviation be? In other words, what would the standard error be? It would be 14.14 because that is 100 divided by the square root of 50. And its shape would be normal. Why? Because the sample size is over 30. If a sampling distribution is normal, we can use the normal distribution table to talk about the percentage of sample means that fall in particular regions, or the probability that a sample mean will fall in a certain place. This will involve using a new ladder, one that starts from X bar and goes down to percentage. The jump from Z to P in percentage is the same here as it was before, but the calculation for Z-score now places a sample mean in a sampling distribution, and it uses this updated formula.